about the differential equation and its solution for the simple harmonic oscillator. So in last class we studied the what is simple harmonic oscillator, what are the characteristics of it, so how the oscillation will takes place, so that we get to know. So now in this session I am going to explain how the particle is oscillating with the displacement equation, that is what is the expression we used to get. So that mathematically also I am going to find out now. So first I have to consider the spring, simple harmonic, any oscillating body. Okay, so consider any oscillating body, that is if you consider a pendulum, so one end is fixed, okay, and which is attached with the bob. Okay, consider a particle of mass m which will execute a simple harmonic motion, So at the mean position the displacement will be 0 and the velocity is maximum, we know. But the extreme point the amplitude will be maximum. So we can extreme point and velocity will be maximum and the acceleration is opposite to the velocity. So suppose y is equal to the a. So the particle is oscillating with the amplitude a. Then m, consider a particle of mass m with the, if y be the displacement of the particle, then the restoring force acting on the body. So that restoring force is always trying to bring the body back to its mean position. So that means that will act in the opposite direction. So from Hooke's law, that we can say, from Hooke's law, force is directly proportional to the negative of the displacement. That means force is acting opposite to the displacement. So if we remove this proportionality constant, then what we will get, F is equal to minus ky, and that negative sign indicates that the particle is moving in the opposite direction, and where k is the here, where k is proportionality constant. That is defined as, that also called as a spring constant. So that, or spring constant, that can be defined as spring constant is force per unit displacement. So then what is the unit? So that is Newton per meter. Okay. So if the acceleration will be, the acceleration is d square y by dt square, then from Newton's second law, F is equal to m into a. So in the, from Newton's second law we know that F is equal to m into a, so that we can write it as m into d square y by dt square. If the acceleration is set up in this simple harmonic oscillator. So we know acceleration is always moving towards the mean position, right? But that is in the opposite to the displacement. If the displacement is positive, then the acceleration is negative, like that, vice versa. So F is equal to m into d square. So now at the equilibrium position, these two forces. So if we consider this equation 1 and 2, so now substituting 1 in 2, we get 1 and 2, then we get minus, that is m into d square y by dt square is equal to minus k into y. So what we got? So by substituting equation 1 in 2, then we got m into d square y by dt square is equal to minus. So now divide the whole equation divide the whole equation by m. So, this equation what we got now. So, divide this equation by m, then what we will get, that is d square y by dt square is equal to minus k by m into y. Okay. So, this we can be written as d square y by dt square minus omega square y, where omega square is equal to k by m. Okay, that is just omega is angular frequency. Omega is angular frequency. So, then this equation will become d square y by dt square plus omega square y is equal to 0. So, this is the differential equation. This is the differential equation. So, this is the differential equation for simple harmonic oscillator. So, next we have to find out the solution for this. What is the solution? That is in terms of y in displacement equation. So, at what displacement the particle will execute the oscillation. So, for that we have to make the some rearrangement of this equation. So, just multiply this equation with the equation with dy by dt. Then we get d square y by dt square into dy by dt plus omega square y into dy by dt is equal to 0. Apply the integration for this equation, then what we will get. So, write it once again, that equation, what is that? D square y by dt square dy by dt plus omega square y into dy by dt is equal to 0. So, apply the integration. Apply integration. So, then what we will get if we integrate this above equation, then d square y by dt square dy by dt plus omega square y dy by dt is equal to 0. So, then what we will get is the integration of this will give dy by dt. So, then already one dy by dt is there, plus omega square y. So, and the integration of constant term, that is integration of 0, that is c, where c is integration constant. This is integration constant. Okay. So, then what we got, dy by dt whole square plus omega square y square is equal to c. So, now we have to find out the constant values by applying by some conditions. So, what is the condition? The particle is oscillating at what condition? That is the displacement will be maximum at the extreme position, at the extreme point, and at the time the velocity, what is the velocity? The velocity is 0, the extreme point. So, when the particle is oscillating, so momentarily it at rest, and then again the particle will come back in the backward direction. Okay. So, at that condition, what is the c value? We have to find out the integration constant value, c value. When the particle is momentarily at rest at extreme point, extreme position, y is equal to the displacement will be maximum, y is equal to a, and velocity will be 0, dy by dt is equal to 0. Okay. So then at this condition, this equation, that is what we will get, that equation will become, so this name we can name it as equation 3. Okay. So this equation 3 will become dy by dt is 0, 0 plus omega square a square is equal to c. So what we got, c is equal to omega square a square. Okay. So now substituting c value in equation 3, substituting c value in equation 3. So we get dy by dt whole square plus omega square y square is equal to omega square a square. Okay. So then simplify this equation, that is dy by dt whole square, take this term to the right side, then what we get, omega square of a square minus y square. Okay. So apply the square root on this, so then we will get the velocity, that is dy by dt is equal to omega root of a square minus y square. Okay. Now separate the variables, then apply the integration, so then we will get the expression for the displacement equation. Now separate the variables, that is dy by root of a square minus y square is equal to omega into dt. So integrate the above term. So that means now what we have to do to get the y value, that is displacement equation, so we have to integrate only. So that's why integrate the above equation. So then what we get, that is dy by root of a square minus y square is equal to omega into dt, right. So integration of dy by root of a square minus omega square is, we know that is formula is the sine inverse of y by a, from trigonometric we know the formula. Then y is equal to omega into, that is omega into t plus integration constant. So here integration constant, that is writing as a phi, because the particle is oscillating with some angle, that is with a phase constant. So here where phi is the integration constant, phi is integration constant or phase constant. Where phi is the integration constant. So this we can write it as sine inverse if y by a is equal to sine of omega t plus phi. Okay. So this again we can write y is equal to a sine of omega t plus phi. Y is equal to a sine of omega t plus phi. That means the particle is oscillating with some total phase, that is omega t plus phi, with the angular frequency with respect to time t, that is in terms of sine angle. So similarly we can get for cos also, that is y is equal to a cos of omega t plus phi. So both are the displacement equation, both in sine angle or in cos angle the particle will oscillate, but here the displacement with respect to time t, that particle is varying sinusoidally with respect to time t with the total phase, that is omega t plus phi, where a is the amplitude with the maximum amplitude, that is E. So this is the solution for the simple harmonic oscillator. So next we have to find out the complex notation, that is in exponential form. What is the expression for the simple harmonic oscillator? So, now we discuss the differential equation and its solution. So, the next complex notation for simple harmonic oscillator or exponential form. Complex, how we can represent in complex notation. Oscillator or in exponential form. Okay. So, again first consider the differential equation. Consider differential equation for simple harmonic oscillator. What we got that? So, consider what is the differential equation we got. So, that is d square y by dt square plus omega square y is equal to 0. Okay. So, this name it has equation 1. So, equation 1 can be written in operator form, in operators. Operator form by substituting that is operators, that is d is equal to d by dt operator. So, and d square is equal to d square by dt square. So, if we open, so then we get that is this will become d square y plus omega square y is equal to 0. The above equation will become d square. So, here what is a comma, y is common, take it outside. So, then we get d square plus omega square is equal to 0. So, here we will get the two solutions, that is one is y is equal to 0 and d square plus omega square is equal to 0. Okay. Then what is the general solution, that is what we will get the value for d is equal to d square is equal to minus omega square, but d is equal to, so root of minus 1 value, that is I imaginary, root of minus 1 is imaginary. So, then we will get I omega. Then what is the general solution for this? Then general solution, so in complex we know that in complex numbers what is the general solution. If we will get the solution that is d is equal to so plus or minus I omega. For this the general solution is y is equal to a into e to the power of I omega t plus b into e to the power of minus I omega t. Okay. So, if y may be the real value. Okay. So, we may get that is real value if suppose a and b are complex conjugate each other. Y where a and b are complex conjugate. And we are complex conjugate. So, that is why then what is that complex conjugate? A is equal to a plus ib and b is equal to a minus ib. Okay. So, if we substitute these values, then the displacement we will get the in terms of real. Okay. So, that is why let us see, then y is equal to, substitute this, a plus ib e to the power of I omega t plus b into e to the power of, so that b value substitute here, a minus ib into e to the power of minus I omega t. So, then what we will get? Y is equal to a into e to the power of I omega t plus ib, if we split this, e to the power of I omega t plus a into e to the power of minus I omega t minus ib e to the power of minus I omega t. Okay. So, now separate the real terms and imaginary terms. Then that is y is equal to A is common, A of e to the power of I omega t plus e to the power of minus I omega t, and the imaginary term, that is I of IB is common, so B also take common outside, then e to the power of I omega t minus e to the power of minus I omega t. So, this is the real and this is the imaginary term. So, that what we got, again write it, y is equal to A into e to the power of I omega t plus e to the power of minus I omega t plus IB of e to the power of I omega t minus e to the power of minus I omega t. So, this is the equation what we got, but here if you observe, this is the real values and this is the imaginary. So, that is why initially when we got, for this general solution may give real values, okay, may give real values or imaginary, but for our convenience we are taking only the real values, imaginary values is not required. So, y is equal to A into e to the power of I omega t plus e to the power of minus I omega t. Okay. So, again in this, when the particle is oscillating, it is exponentially increasing and exponentially decreasing will be there, but so if we consider, we can take the positive exponential, that is then what we will get, y is equal to A into e to the power of I omega t, but for the total phase of the particle means then we have to add exponentially with the phase constant, that is I of omega t plus phi, exponential of e to the power of I of omega t plus phi. So, this is the expression when the particle is exponentially, that is when the particle is oscillating, so exponentially e to the power of I of omega t plus phi. Omega t plus phi is the total phase of the particle, e to the power of I of omega t plus phi. So, this is the exponential form in the case of simple harmonic oscillator. With this displacement equation, the particle is oscillating exponentially, where phi is the phase constant. So, first go for the expression for the velocity. Find out the expression for velocity. So, we know that when the particle is oscillating, at the mean position, so at the mean position the displacement will be 0 and the velocity will be maximum. So, in this case of a simple harmonic expression for velocity in simple harmonic oscillator, So, in this case, what is the expression for the velocity? And next we have to find out what is the acceleration for this case. So, that we have to find. So, first we know the displacement equation for simple harmonic oscillator. So, what is the displacement? Displacement equation for simple harmonic oscillator. So, we already derived the expression for the simple harmonic oscillator, that is differential equation and solution. So, displacement equation for simple harmonic oscillator, what we got, y is equal to A sin of omega t plus phi. So, where A is the amplitude. So, at the harmonic oscillator is oscillating with this displacement, y is equal to A sin of omega t. So, velocity, what is velocity? We know it is the rate of change of displacement. Velocity is rate of change of displacement. Rate of change of displacement. So, therefore, we have to differentiate this equation. So equation 1, name it as equation 1. Now differentiate equation 1. Then what we will get? Dy by dt is equal to, so with respect to t we had to differentiate. So constant term, write it as it is, a is constant. Sine of omega t plus phi. The differentiation of sine of omega t plus phi is cos of omega t plus phi. And with respect to t we are differentiating, so that's why write the coefficient of t, that is omega into omega. So then, so this is the velocity what we got, v is equal to a omega cos of omega t plus phi. So name it as equation 2. Okay. So next, so to find out the velocity expression, just we can, suppose if we write again this equation in terms of angle, then what, how we can write, that is in terms of sine. So we can write this equation as also v is equal to a omega sine of omega t plus phi plus pi by 2. That means we know that sine of 90 plus theta is cos theta. So that just we are writing in terms of sine with the some angle. So omega t plus phi plus pi by 2. Just keep it as it is. So now if we compare this equation, displacement equation and velocity, then the phase difference between the displacement equation and velocity is, that is 90 degree. So to solve this equation, to find out the expression for velocity, just consider that we know that sine square omega t plus phi plus cos square omega t plus phi is equal to 1. Okay. But we have want in terms of cos, so that's why keep this cos square omega t plus phi here, and then okay, write this in right side, that is in RHS, bring this term to the RHS, then what we will get? 1 minus sine square of omega t plus phi. Okay. So this equation we can be write as cos of omega t plus phi is equal to root of 1 minus sine square of omega t plus phi. Okay. But what is this sine of omega t plus phi? We know that from equation 1, sine of omega t plus phi that will give is equal to y by displacement by amplitude. So now, so substituting this in the above equation we get, therefore we get cos of omega t plus phi is equal to root of 1 minus y square by a square. So that is root of a square minus y square divided by a square. So this we can be write as a square minus y square divided by a. Just take this a outside the root, then the square and root will get cancelled, we get a. So that is what is cos of omega t plus phi value. Okay. So now substitute cos of omega t plus phi value in equation 2. So now by substituting equation 3, equation 3 in 2, we get v is equal to a omega root of a square minus y square divided by a. So that a will get cancelled. So what we got? V is equal to, so that will give v is equal to omega root of a square minus y square. So this is the expression for velocity when the particle is oscillating, okay, when the particle is at the extreme position, so then what is the velocity, or okay, so this is the expression for the velocity for a simple harmonic oscillator in general case. But at mean position, so we know that the displacement will be 0. So at that condition, what is the velocity? So at mean position, displacement will be 0. At mean position, displacement will be 0. So then what we got, then the velocity will become v is equal to omega root of a square minus 0. So that we will get, so this root square will get cancelled. So we will get v is equal to a omega. So this is the velocity will be maximum. So at the mean position, the displacement is 0. So in that case, the velocity will be maximum. So what we got, V max is equal to a omega. So at this position, the velocity will be a omega in simple harmonic oscillator. Okay. But the general expression for velocity for simple harmonic oscillator, V is equal to omega root of a square minus y square. But in the mean position, at mean position, the velocity will be v is equal to a omega. So this is the expression for velocity. Next, similarly we have to find out the expression for acceleration. So again consider the displacement equation, but here we have to differentiate twice, then we will get the acceleration. Now similarly find out the expression for the acceleration in case of simple harmonic oscillator. So just now we find out what is the when the particle is oscillating at the main position, what is the velocity, that velocity will be maximum, that is equal to a omega. So next, acceleration. Similarly consider the displacement equation. Displacement equation for simple harmonic is y is equal to a sine, is equal to a sine of omega t plus phi. The velocity, the acceleration is rate of change of velocity, rate of change of velocity. So that gives, so differentiate the ones, if we differentiate, then what we will got, we got the velocity, that is a omega cos of omega t plus phi. So again differentiate this, so then what we will get, so that is acceleration. So that will gives dv by dt is equal to a omega minus cos of omega t plus phi is minus sine of omega t plus phi, and with respect to t we are differentiating, so then what is the remaining term, that is omega, right, as it is. So what we got, so that is minus a omega square sine of omega t plus phi is equal to minus a omega square sine of omega t plus phi. But from equation 1, what is sine of omega t plus phi? From equation 1, sine of omega t plus phi is y by a. So that we can write here. Then next what we get, dy from equation 1, so sine of omega t dv by dt is equal to, so from equation 1 we get dv by dt is equal to minus a omega square y by a. So that a will get cancelled. So then what is the acceleration we are getting? So that acceleration is equal to minus omega square y, So acceleration. So that means the acceleration is negative to the displacement, right? So if we generally writing, well, if we ignore the negative sign, then what we get, acceleration is equal to omega square y. So if we observe here, and this acceleration we are getting minus a omega square sine of omega t plus phi. So then what angle exactly the particle is oscillating with the acceleration. So that minus sign, we can eliminate that minus sign by, that is acceleration, what it will gives dv by dt is equal to, we can write that equation as, so just name this as equation 2. So equation 2 can be written as, equation 2 can also be written as equation 2 also can be written as a omega square sine of omega t plus phi plus pi. That is sine of 180 plus theta. Sine of 180 plus theta is minus sine of omega t plus phi, because sine of 180 plus theta that will comes in the third quadrant. In third quadrant, if the sign is negative, then the so minus minus will get cancelled. So then what we will get for sine of 180 plus theta, that is acceleration is equal to a omega square sine of 180 plus theta. So this is also the expression, that is in terms of angle, with what angle. So then what is the phase difference here between the displacement equation and the acceleration? So that is 180 degree, right? So exactly 180 degree phase difference between displacement and acceleration. So totally the acceleration will be maximum at this time. Okay, the acceleration is maximum. The acceleration is maximum at acceleration is maximum. The acceleration is maximum when dv by dt is equal to a omega square sine of omega t plus phi plus pi, or this way can also acceleration is equal to what we got, a omega square. So this is the expression for acceleration. The particle is oscillating, acceleration a omega square. So the velocity is a omega, and the displacement, that is if we take only the magnitude, then y is equal to a. Okay. So at mean position y is equal to 0. So next, what is the phase difference? What is the phase relation between displacement, acceleration and velocity? Next is phase relationship between velocity between displacement velocity and acceleration. So till now we derived the expression for displacement equation and velocity and the acceleration. So by writing that, we can find out the with what angle the particle is oscillating. So that is, for a displacement equation, we know, write the displacement equation, y is equal to a sine of omega t plus phi. Okay. So and for velocity, v is equal to a omega cos of omega t plus phi, but in what angle, that is the angle, that is v is equal to a omega sine of omega t plus phi plus pi by 2. So what we got, that is, again I am writing with the angle 90 degree. Acceleration, so that what we got, acceleration is equal to a omega square sine of omega t plus phi plus pi. Okay. So now So this is the displacement equation 1 and velocity expression 2. If we observe this three expressions, that is displacement, velocity and acceleration, so then we can easily analyze at what angle, at what phase difference the particle is oscillating. So now the phase difference between velocity, displacement and velocity, that is between displacement and velocity is, so the angle is, that is pi by 2. That means the velocity leads the displacement by, the velocity leads the displacement by pi by 2, right. So exactly the velocity, so that is in quadrature we can say, because exactly that is in quadrature. So that means if the displacement is like this, then what is the velocity? So quadrature, so that what its angle it forms, that is exactly in quadrature form, 90 degree. So 90 degree, pi by 2. The phase difference between the velocity and displacement is quadrature, pi by, so leads, so that means it leads by 90 degree. Then if we write the displacement lags the acceleration by pi by 2, we can say in that, like that also state, the displacement lags the velocity by pi by 2. Okay. So similarly, next, what is the phase difference between acceleration and velocity? That is the, if we compare this, the acceleration leads the, similarly if we, what is the acceleration, the acceleration leads the velocity, what is the phase difference between the acceleration and velocity? So that we can say that velocity by, what we got, pi minus pi by 2, right. So 2 pi minus pi, that is pi by 2 we will get, so leads by pi by 2. The phase difference between the acceleration and velocity, that is pi by 2. So that's why we can say that acceleration leads the velocity by pi by 2. So here if we see the acceleration and the displacement lags the acceleration by phase difference pi. So here the acceleration leads the velocity by pi by 2. Okay, that is a phase difference. If we compare the phase difference between acceleration and velocity, that is by pi by 2. Okay. So similarly, acceleration and velocity, what is the phase difference? So that is the displacement lags. Here we can say that the displacement lags the acceleration by pi, phase difference pi. So what we got, that is pi. So this is the phase relationship between the velocity, displacement and acceleration. So next we have to show this by the graphical representation. So now same, we are showing graphical representation of displacement, velocity and acceleration. So again, once again consider the three equations. So consider expression for displacement, velocity and acceleration. What we got for displacement, y is equal to a sine of omega t plus phi, and for velocity v is equal to So V is equal to A omega. So just that is A sin of omega t plus phi is there, plus pi by 2 is there. So that is if we consider only the A omega, right. So if we consider only the, take the magnitude. So V is equal to A omega, that is a maximum. The displacement will be maximum at y is equal to A sin of omega t plus, and the velocity will be maximum, V max is. So similarly acceleration. So what is the acceleration? Acceleration A omega square sin of omega t plus phi plus pi is there, right. So so if we consider take only the magnitude A omega square. So similarly in displacement equation, if we consider only magnitude is, that is only amplitude, y is equal to A, it will give y is equal to A. Okay. So hence for at y is equal to 0, at when the displacement will be 0 at the mean position, then the velocity V is equal to A omega V max. And what is the acceleration? The acceleration is also 0 at mean position. So when the displacement will be maximum, so at the time the amplitude will be y is equal to A, and the velocity will be 0. And what is the acceleration? So acceleration is opposite to the displacement in sign. So that's why here what will come? Negative will come, right, minus A omega square. And when the displacement will be negative, so at that time the acceleration will be positive, A omega square. Okay. So when the displacement will be maximum, so at that time the velocity will be 0, and when the displacement will be 0, at the velocity will be maximum. Okay. So and the displacement and acceleration magnitude is in opposite, that in sign it is in the opposite sign. If it is positive, then the acceleration will be negative. When the displacement is negative, at the time acceleration will be positive. So graphical representation graphically as shown below. As shown below, how we can represent the displacement equation will start from the origin when the particle is oscillating with respect to time t at instant of time t. So the displacement, that is the amplitude, if we represent that is by the amplitude. So this will show, and so in negative axis it will represented by minus A. Then the velocity, so when the displacement will be 0, the velocity will be maximum. So that's why the graph can be shown. So this is the velocity. So what it this is the displacement and this is the velocity. And next the acceleration is opposite to the displacement but in the negative axis. So that we can represent it by opposite to the displacement. So, this is the displacement acceleration. So, velocity, what the velocity, that is a omega, and what is the acceleration? That acceleration is a omega square. The particle is oscillating at the mean position with the acceleration, when the acceleration will be maximum, a omega square, and when the displacement will be maximum, at the time the magnitude is a, and when the velocity will be maximum, at its magnitude with a omega. So, the graphically how we can represent the phase relationship between the velocity, acceleration and displacement also. So, if you observe here, the displacement and the velocity is exactly the phase differences, that is pi by 2, it is in quadrature, and the displacement and acceleration, the phase difference between the displacement and acceleration is 180 degree. So, right, 180 degree. Displacement and acceleration phase difference is pi, and the displacement and velocity, that is quadrature, pi by 2, exactly pi by 2. So, like this graphically we can represent the relationship between the velocity, acceleration and displacement.